Good morning. This is our fifth class on Unit 4 Magnetic Properties of Solids. In today's session, we are going to learn about ferromagnetic domains and anisotropy energy. Okay, this is just theory, so first we will read all those things and I will explain in its sentence that it is confusing. Okay, so at temperature well below Curie point, electronic magnetic moments of a ferromagnet are essentially parallel when regarded on a microscopic scale. At looking at a specimen as a whole, magnetic moment may be very much less than the saturation moment, and the application of an external magnetic field may be required to saturate the specimen. The behavior observed in polycrystalline specimens is similar to that in single crystals. Okay, meaning of that paragraph is that is at temperature below Curie point at T less than Tc, magnetic moments in the case of a ferromagnet will be parallel. That is, they will be aligned in a parallel direction, or they will be aligned in the direction of field when you are looking it on a microscopic scale, not on a macroscopic scale. Okay, that is from a small field of view. When you look at a ferromagnetic material, all the magnetic moments in it will be aligned in the direction of the applied field. Okay, but if you look at the specimen as a whole, that is, if you are looking at the specimen as a whole means if you are looking at it at a macroscopic scale, okay, not a single region, you are looking it on the specimen as a whole, okay, then the magnetic moments, how will the magnetic moments will look like when you are looking at the specimen as a whole? They will be very much less than the saturation moment, and when you apply an external field, they will come to the state of saturation. Okay, now this behavior is the same in the case of polycrystalline material as well as in the case of single crystalline material. Okay, now actual specimens are composed of small regions called domains. Within each of these domain, local magnetization is saturated. So what is meant by domain? Domain is nothing but a very small region in a ferromagnetic material where local magnetization is saturated. That is, all the magnetic moments are aligned in the direction of the field and the magnetization of the specimen as a whole will be saturated. Okay, the direction of magnetization of different domains need not be parallel in many cases. Now, an arrangement of domains with approximately zero resultant magnetic moment is shown in this figure. See, here the magnetic moments are aligned in different direction. One is aligned in this direction, other is in this direction, this one is in this direction. So all of these magnetic moments are arranged in different direction. That means they are all in random orientation. Okay, so what will be the resultant magnetic moment? Definitely it will be zero. So this is just an example of a domain. Okay, domains can also be seen in not only in ferromagnetic material but also in antiferromagnetics, ferroelectrics, antiferroelectrics, ferroelastics, superconductors, and sometimes it can also be seen in metals under conditions of strong de Haas-Van Alphen effect. Okay, that is this domain. What is meant by domain? Domains are small regions where local magnetization is saturated. The direction of magnetization of different domains need not be parallel. Okay, so that is a domain. It can be seen in all these types of materials. Now, the increase in uh, gross magnetic moment of a ferromagnetic specimen in an applied magnetic field takes place by two independent processes. That is, development of magnetic moment in a ferromagnetic material. That is, when you apply a magnetic field, we have said ferromagnetic material, when you apply a magnetic field to a ferromagnetic material, it will get magnetized. That is, magnetic moments will align in a particular direction and the material will get magnetized. And that magnetization arises by two independent processes. Which are they? That is, in a weak applied field, volume of domains will orient with respect to the field increases at the expense of unfavorably oriented domains. That is, when you apply a weak field, domains which orient in the direction of field will increase when compared with the domains which orient unfavorably with respect to the field. Okay, that is domains which orient in favor of the field will increase when compared to domains which orient not in favor of the field. Okay, then that is in the case of when you are applying a weak field. Now what happens when you apply a strong field? Then the domain magnetization rotates toward the direction of field. Okay, so these are the two conditions that happens when you apply weak field, and what happens when you apply strong field. When you apply weak field, domains which orient in the direction of field will increase when compared to domains which orient opposite to the direction of field. Okay, now when you apply strong field, magnetization will rotate toward the field direction. Okay, that graph is shown here. Now here you can see a hysteresis loop. Now the technical terms defined by hysteresis loop is shown in the figure. One is coercivity HC. What is coercivity? It is the reverse field that reduces magnetic field B to 0. Okay, and then next one is remnants. It is a value of magnetic field at H is equal to 0. So here these are the two terms that you come across in the case of hysteresis: coercivity HC and remnants BR. Okay, coercivity is the reverse field that reduces magnetic field to 0, and remnants is the value of magnetic field at H equal to 0. H means applied magnetic field strength. Okay, coercivity is defined as reverse field HC that reduces the induction B to 0. I have already explained, starting from saturation. Now, in high coercive materials, this coercivity HC is defined as the reverse field that reduces magnetization M to 0. Okay, here it was that reduces induction B to 0. Here in this case it will become that reduces magnetization M to 0. So you can study any one definition on coercivity. Now some of the applications of the presence of domains in ferromagnetic material. One is in the case of transformer core. That is, in a transformer core, loss must be less. Okay, in taking core around a cycle, that you know. This means we must need a material with a low coercivity, or a material that offers high permeability. By making pure homogeneous and well-oriented material, we will be able to fabricate domain boundary displacement and thereby attaining high permeability. That is how we obtain high permeability, or that is how we obtain material with a low coercivity. Low coercivity means high permeability. Here they have given an approximate value of relative permeability. No need of studying that. Now, in a permanent mat, high coercivity is needed. Okay, in the transformer core, in order to reduce losses, we must need a material with low coercivity. That means we need a material with a high permeability, and here they explained how high permeability is attained. Next one is, in the case of permanent magnet, we need material with a high coercivity. Okay, now how it is achieved? It is achieved by suppressing boundary displacement. Okay, that is how to suppress boundary displacement. It is done by eliminating domain boundaries. That is, we know we don't need domain boundaries. Domain boundary means here if you have a domain, there is another domain. That is, this is the domain boundary. That is, if you want a material with a high coercivity, you have to suppress this domain displacement. That means you don't want this domain boundary. Okay, now this is achieved in very fine particles or crystallites that consist of a single domain, okay, without the boundaries. By controlled precipitation of second metallurgical phase, the specimen may be heterogeneous on a very fine scale. Characteristically, there is a critical radius below which single domain attributes are formed. No need of learning that, this much is enough. Okay. That is, these are the applications of domain at is where the region where you need material with low coercivity, and the region where you need material with high coercivity. Low coercivity in transformer core, purpose and how it is achieved. High coercivity in permanent magnet, purpose and how it is achieved. Okay, up to this much is enough. Now, anisotropy energy. There is an energy in ferromantic crystal which directs the magnetization along certain crystallographic axis called direction of easy magnetization. This energy is called magnetocrystalline or anisotropy energy. It does not come from pure isotropic exchange interaction considered thus far. So just study this. What is meant by anisotropy energy? Now they are giving an example of a hexagonal crystal, say cobalt. Here the direction of easy magnetization is hexagonal axis because it is having a hexagonal structure. At this, everything is discussed at room temperature. Okay. The magnetization of the crystal sees the crystal lattice through orbital overlap of electrons. The spin interacts with the orbital motion by means of spin-orbit coupling. In cobalt, anisotropy energy density is given by. So first you write this definition. What is anisotropy energy? Then start saying with an example of cobalt. Then after that write this sentence. In cobalt, anisotropy energy is given by this expression. UK, that is anisotropy energy in the case of hexagonal crystal cobalt equal to K1 dash sine square theta plus K2 dash sine raised to 4 theta. Here what is theta? Is the angle the magnetization makes the hexagonal axis. Now just mention the room temperature values of K1 dash and K2 dash. Okay, that is enough. Then another example. Here now they are taking a cubic crystal, example iron. Okay, and here the direction of easy magnetization will be cube edges. Okay, because it is having a cubical shape. Now to represent anisotropy energy of iron, that is first we have taken a hexagonal crystal cobalt and you have written its corresponding anisotropy energy. Okay, there the direction of easy magnetization was hexagonal axis. Now you are taking the case of a cubic crystal iron. Here the direction of easy magnetization is the cube edges, and now you are going to write the expression for anisotropy energy of cubic crystal iron. Okay, to represent the anisotropy of energy of iron magnetized in an arbitrary direction with direction cosines alpha 1, alpha 2, alpha 3 referred to the cube edges, we are guided by cubic geometry. The expression for anisotropic energy must be an even power of alpha I. So here three direction of cosines alpha 1, alpha 2, alpha 3 are taken into consideration to express the anisotropy energy of cubic crystal iron. Okay. The expression for anisotropy energy must be an even power of alpha I. All these are summarized to alpha I. Okay, and one condition is that opposite ends of the crystal axis are equivalently magnetized, and it must be a constant, that is it should not change under the interchange of the direction cosines. Okay, so that is the condition. And the expression for anisotropy energy must be an even power of alpha I, and provided the opposite ends of the crystal axis are equally magnetized, and it should be a constant, that is it should not be vary under the interchange of the direction of cosine axis alpha I. Okay. Now the lowest order combination satisfying this type of geometry is given by this alpha 1 square plus alpha 2 square plus alpha 3 square. The next combination is the fourth degree, that is this one, alpha 1 square alpha 2 square plus alpha 1 square plus alpha 3 square plus alpha 3 square alpha 2 square. Then comes the sixth degree, like that it goes. So thus we can combine this fourth degree and sixth degree to write the expression for anisotropy energy UK of cubic crystal iron. Okay, now the value of K1 and K2 is this one in this case, in the case of cubic crystal. So this is the expression for anisotropy energy in the case of hexagonal crystal. Then write these two values. In the case of cubic crystal like iron, the expression for anisotropy energy is this one with K values, this K1 and K2. This one is the fourth degree combination. This is the sixth degree combination. So just mention the crystal type, then the direction of easy magnetization, and then directly write the expression for anisotropy energy. That is enough. Okay, thank you.